All right, so let's talk about heat. And heat is like light in that the uh, light is the absence of, or darkness is the absence of light, and cold is the absence of heat. And that's just something to keep in mind, that heat is sort of the thing that is flowing from the thing that is warmer to the thing that is colder. There is no such thing as like cold movement or that kind of thing. And then I apologize for this being in the way, but unfortunately, I've learned that for some reason, let's see if that works up there. If that ever disappears, then I'm going to get angry. All right. Heat is not showing up. Heat is energy transferred between objects at different temperatures, and temperature, you recall, is the average kinetic energy of a substance. We said heat was Q, and I've given up on that. I'm going with heat is joules. We just go with J, and it makes more sense that way, I think. And when you're canceling units to figure out how to find heat, it's helpful to just think of heat as joules. I don't know why we throw the Q in there. Temperature is T. That's somewhat helpful. And we measure temperature in degrees Celsius or Kelvin, and we have to calculate heat, whereas temperature we can use to calculate heat, but it's measured with a thermometer, and it's related to heat. But as you recall from the lab where you're touching things in the oven, it's not absolutely the temperature that determines whether or not you burn yourself. So heat flows in one direction from something with higher temperature to something with lower temperature. And we brought up this equilibrium idea that in the lab where we took the hot metal out of the boiling water and put it in the cold water, the water and the metal equilibrated. In both cases, actually, when it was in boiling water, it was the same temperature as the water. It was 100 degrees Celsius. And when you put it in the cold water, it would warm up the cold water and the metal would cool down until they reached the same temperature. So, and that was true also when we burned the Captain Crunch. The can and the water were in equilibrium. They were the same temperature to start, and after heating up, they were the same temperature because they were in contact with each other. All right, so a substance gains heat, we would say it has a positive value, and if it loses heat, it would have a negative value. And here's the equation that you really need to know if you don't like to cancel units, and that is that heat is equal to the mass times the change in temperature times the specific heat. And that makes a lot of sense, as I've told you. The key here is that change in temperature, right? That it's the difference in temperature. It's not just one temperature that you use. All right. So the specific heat, if I ever ask you for a definition of that, is the energy required to raise the temperature of 1 gram of substance 1 degree Celsius. Hence the joules, the heat required to raise 1 gram, the gram, for 1 Kelvin. So the units are joules over gram Kelvin or joules over grams degrees Celsius. And this is telling us that how much heat can be transferred from something depends on the kind of material that's changing temperature, right? You can grab on the styrofoam in an oven and not hurt yourself. You can grab on the wood in an oven and probably still not hurt yourself. The issue is if you grab onto some metal or glass or tile, then you might hurt yourself because those things hold heat better than the others that I mentioned earlier. The mass of the material changing the temperature is also important, right? Because there's a gram thing here. So, and that's part of the reason styrofoam doesn't do a job on your hand, is there's not a lot there to do much. And then finally, the change in temperature. If you're grabbing something that is room temperature, it's not going to hurt your hand. It's not going to feel cold or warm. It's just when there's a big difference in temperature that you will feel something. All right. So a high specific heat we talked about means that pound for pound, it'll hold more energy. Um, so plastic actually does have a high specific heat, right? And styrofoam does, but the problem is the pound for pound, that the density of these things, I mean, even air has a high specific heat compared to the metals that you were touching. But it's hard to get a lot of air to touch your hand at one time. And that's why it, to have the same mass of air as you do of iron in an oven, right? An iron bar, to get the same mass of air to do the damage that an iron bar would do, you would need just whole bunches of air compressed into a little area. And that's not common. So, and a low specific heat tends to mean that it takes a lot of energy It doesn't take a lot of energy to heat it up, and it doesn't take long for it to cool down. That's basically what these mean. A larger specific heat means it takes a lot of energy to heat it up, and it takes a long time to cool down. And that should be obvious. So here are some things that we would do. Actually, before we get into that, let's discard those. Let's hope that this keeps rolling. But let's get into this. So heat transfers, going back to that thing, things are wiggling around, and that's what temperature is, right? And so heat transfers when one of these things that are wiggling interacts with another one, and they change their energy. So some of the energy is transferred from this blue ball into that yellow particle, and by doing that, the energies sort of become similar, but the blue particle loses a little energy and it gives it to the yellow particle, and that's how heat is transferred. That's how the energy is transferred. So what you need then is for, on a very microscopic scale, and this is basically going to be much of what I ask in the short answer section, right? These things that are moving fast out here, to have any effect on the air outside the coffee cup, have to transfer their energy to the cup, and then these things wiggle around, and then that wiggling has to be transferred to the air. In order for that to happen, one of those air particles has to hit the cup and then pick up some of that energy and then move around with a little more energy than it had before, and that's how heat is transferred. So you need this sort of interface to happen, and that's what the difference is between styrofoam and a metal in the oven. Styrofoam does not have near as many particles in it as metals would, like copper or aluminum, and so there's more particles moving to affect your hand or whatever it is that you're touching them with, or the ice, as we did, right? We had cubes of ice that we were melting with the things. So the more particles you have to be moving around, the more it's able to transfer that energy to something else. And that is ultimately what's going on a small scale there. All right, back to this. Hopefully it's still working. Seems to still be working. And so here's an example where we can use this equation, but I've tried to let you know everything you need is in the formula here. So calculate the amount of heat. So we're looking for joules, right? And we're given the specific heat. So that's 0.449 joules over grams degrees Celsius. So if we wanted to get joules out of that number, it should make sense to you that we would need to multiply it by grams so that the units of grams cancel, and we would want to multiply it by degrees Celsius. The degrees Celsius cancels. And then that thing that is left would be joules. So if we look in our equation, we have 50 grams. So that means we're going to multiply it by 50. And we have a temperature change from 20 to 80, which is 60 degrees Celsius. So you can just use this equation and memorize that equation, that heat is always equal to take your mass, take your change in temperature, take your specific heat, and multiply them all with each other. But I will always give you these units. And if I'm asking you for heat, I'm looking for joules. And if I'm looking for joules, that means you have to take that number and multiply it by grams to cancel the grams, and multiply it by Celsius to cancel the Celsius. And that'll give you the answer. And I don't think I have, there it is, my calculator too handy. But if we do all that, and I think, no, I didn't put anything up for this, but 0.449 times 50 times 60 gives you 1,347, which should be to three significant figures, so 1,350 joules. But again, I don't go nuts with the significant figures right now. Let's just try to get this concept down. All right, moving on. So what's the mass of a piece of copper? So we're looking for the mass here if you're doing the equation. And we have 566 joules of heat cooling from 77 to 22. So our difference in temperature, our delta T, is going to be 55 degrees Celsius. And again, if we're trying to figure out the mass, we're trying to figure out the grams, it should make sense to you that since in this specific heat equation, grams is on the bottom, we're going to want to flip that around. So it's basically grams degrees Celsius over 0.385 joules. And we would want to multiply the joules out So that is 566 joules. That'll get rid of the joules. And we're going to want to multiply by 1 over the change in temperature to get rid of the Celsius. So 55 degrees Celsius would go on the bottom to get rid of that. And now the only thing left is grams. And so we multiply 0.385 times 55, and whatever that is, we divide into 566. So 566 divided by 0.385 equals a larger number, and then divided by 55 is a smaller number, so it's 26.7 grams. So the other way you could do it is to set this up where joules, which is 566, is equal to the mass, which is the x that we're looking for, times 55 degrees Celsius times 0.385 joules over grams degrees Celsius. And when we're trying to solve for this x, we would divide the 566 by the 55 and the 0.385. You really got to be decent with your algebra here for this unit. All right, moving on now to this thing, and I think very helpful for that was, I think at least, was this little activity that many of you hated. But it was a quick, you have to admit, it didn't take long. So what we did here was we experimented with a few things, and you could choose a substance, and what you were supposed to witness as the substance was heated up was, at first it heats up, it changes temperature, and then when it's melting, as you can see here, the temperature stays the same. It's right there at 47, and that keeps going until it becomes all liquid, and then it heats up again, and then it stops heating up again when it boils. So whenever there's two phases present, the temperature does not change. So the melting temperature of this purple thing was 47. That's even, you can see here, it was between 40 and 50, and it's on the higher end of 40. So 47 was the melting temperature, and the boiling temperature, where you have gas and liquid both present, was 143. And again, the thing went flat. So you can check that and says, well done. And we can switch then to the green balls and see how that works. And you should see the same situation. So you heat up a solid, and the solid gets hotter and hotter until it melts. And at the point where it melts, it's going to level off its temperature right now at 30. And then when all the melting is done, now you're just heating liquid up more and more and more. And then when the liquid is boiling, then it's going to flatten off again. So our melting temperature in that case was 30, which was that first plateau, and our boiling temperature was 121, where that second plateau was. Right? Right. All right. So that is what that was. I think we can turn that off now. And so to finish up, we have what's called a heating curve, and at parts A, C, and E is where temperature is changing, right? And B and D are where temperature is not changing. So A, everything's a solid, and it's heating up the solid, and then at B, you're melting that solid, so the temperature is not changing. And then at C, you're all liquid at that point, so you can heat up the liquid, and then at D, you're boiling that liquid, and then that doesn't change the temperature until you get to E, where the liquid's all a gas, and then you're just heating up the gas. So the melting point, the boiling point would be where this thing is flat up on top, and the melting point would be where this is flat on the bottom. All right, and why does that happen? Because when a solid becomes a liquid, and we tried to demonstrate this with people like locked arms, whereas people are just holding hands, all that energy that is not changing the temperature that is going in is making these particles have more mobility, basically, a little more freedom of motion. So the average kinetic energy, the motion of, if you had a thermometer in there, how much force these balls would be hitting the thermometer, is not changing. What's changing is just the ability of where the balls can go, where the particles can move. And the same thing happens when liquid becomes gas. These particles are now having enough energy to go into like a higher part of the flask or the container, and in doing so, that's a greater degree of freedom. All right, this wants to switch around. So when you are dealing with melting or boiling, you're going to need this heat of fusion and this heat of vaporization. And heat of fusion deals with going from solid to liquid. That will always be given to you. We only use water for this class, so it's 334 joules per gram. It's endothermic when you go from solid to liquid, and it's exothermic going back from liquid to solid. And I showed you that little Game of Thrones clip that was supposed to show you that when he takes solid gold and melts it, it took energy. He had to put that on the fire. And then when he takes the liquid gold and makes it turn back to solid, it releases all that energy as heat, and the heat does some damage. So heat of vaporization, this was hard to teach years ago, but vaping is turning a liquid to a gas. So hopefully you're familiar with that now. So heat of vaporization is the energy required to go from liquid to gas. And as you can see, that's generally larger than the fusion energy, because the degree of freedom that you have in a gas, shown here, from a liquid, that's a pretty big difference in freedom versus a solid, which is just on one half of the container, and a liquid, which just spreads it out to the lower part of the container. Anyway, that's that. So when you're in these places where temperature is changing, then you need that delta T, and that means you use the specific heat to find those energies. And when you're flat, you're just going to use this much easier equation where you just multiply the mass times one of those delta H's. So here is a question: how much heat is absorbed when 8.75 grams of water boils at 100 degrees? So boils is the key word here. That's a change in state. So we're going to have to use one of these things because it's changing state. It's at a flat part. There is no change in temperature. The fact that a temperature is listed is a red herring, right? That's just trying to get your attention away from the fact that you're supposed to use the equation where you multiply one of those delta H's by just the mass. And in this case, since we're talking about boiling, that's liquid to gas, that means it's vaping. And we take the mass times the joules per gram. And again, if you think about it, this is joules over grams, right? If I cross that out, so it looks like that, and grams will cancel, and that gives you joules. So it makes sense that that's what you would do. You can memorize this equation if it makes you feel better, but the reality is that unit of measure, which I give you, will tell you what to do with it if you need joules, which is multiply it by grams. So we already talked about that. And then here, if we're running and we're sweating, what happens to all that sweat? So we have 500 grams of water lost due to sweating. It's evaporated. That's a change in state. So we're going to use that heat is equal to the change in H times the mass. And the H we're going to use, since it's evaporating, is the vape. So hopefully I do that there. So 500 grams times, again, if it looks a little better like that, 2260 joules per gram. This number will be given as the delta H vape. I will tell you that on any test or quiz that the delta H vape is 2260 joules per gram. So that means multiply it by grams and you can get joules. And that's how many joules, 1.1 million joules of energy are taken away from your body when you sweat, ideally, not in North Carolina though. So the trick to these is trying to figure out, which do I use? Do I use this equation or this equation? And the things you're looking for are, if a change in state is mentioned, then you're going to need to use an equation with a delta H. If a change in temperature is mentioned, change in temperature is important for that specific heat one. So for this first one, ice is solid water. So you're going to want to use this specific heat. You want the mass that's given in the equation, 250 grams, and the delta T would be the 40 to 0. So you would say that is 250 grams times 40 degrees Celsius, which is the difference from minus 40 to 0. And the specific heat is 2.06 joules over grams degrees Celsius. And that's why those cancel, and you're left with joules. For this one, though, melting, the temperature there is another red herring. So don't buy into that. You just need to use this very simple equation. And right here, you can see heat of fusion is given. Since it's melting, it's fusion. It's not vaping. Vaping is liquid to gas. Melting is solid to liquid, and that's fusion. So it's 334 joules over grams. And if I wanted to get joules out of that, I need to multiply it by grams, which in this case is 250 grams. And that'll cancel that way. And you just multiply those. All right. So on this next one, there's some answers. My scribbling. So for this next one, if you look at this, how much heat is needed to increase the temperature 250 grams from 20 to 100? Now, is there a change in state involved in this problem? So we're looking at this problem up here. Is there a change in state? The answer is, since you see a change in temperature, no. It also doesn't mention boiling or melting or evaporation or anything. So we have a delta T, and that delta T is 80 degrees Celsius, and that means we're going to need to use the specific heat, and the specific heat we're using is water, which would be liquid at that point. I'll be a little clearer with this on the test. So 4.18 joules over grams degrees Celsius, and it's looking for heat, so it's looking for joules. That means we need to multiply that by the grams, 250 grams, and by the degrees Celsius, which is 80 degrees, the change in temperature. And did I give a thing there? No, I didn't. All right. You can do that out. That's fine. All right. How much heat is there needed? It's 11 o'clock at night. And I just saw Pippin, which was wonderful. All right. Here we're talking about boiling. Boiling means a change in state. There's one temperature given, but not a change in temperature because it's boiling and there is no change in temperature. So you're going to need to use either the fusion or the vaporization. Boiling is turning a liquid to a gas. So hopefully that indicates to you to use the vaporization, H-vape. So to take 2260 joules over grams, and I need joules because I'm looking for heat, I would have to multiply that by grams. So that's 250 grams. And the grams cancel. All right. So last thing we covered is, again, with these states of matter, melting, evaporation, sublimation are all increasing energy. So that means they are, if they're going up, endothermic. And then the things that are going down are pulling energy out. So condensation or freezing is pulling things out. So those are exothermic if they go down. So the blue processes are exothermic and the red processes are endothermic. And that was that. So I hope that makes sense. I'm going to go to bed. I hope you have a nice weekend, and this is what we'll do Monday.